Okay, we've got the Math 1050 final exam review. This is going to be very similar to what you'll see on the final exam. These questions, like I said, are very similar. Question 1 here, find the difference quotient. This comes from section 2.1. Now the way I like to do this is to break this problem down into pieces. We have f of x plus h and an f of x. So obviously we know f of x is negative 2x plus 5. And f of x plus h now f of x plus h means that this x plus h replaces that x. So it's going to be negative 2, and then instead of an x, it's going to be x plus h plus 5, and that's negative 2x minus 2h plus 5. So now we have both pieces in the numerator here. We've got f of x plus h here, and we have f of x. So to set up the difference quotient, we need a quotient, and f of x plus h goes here. So that's my negative 2x minus 2h plus 5, and then it says I'm supposed to subtract f of x, and f of x is that function there. So that's subtract negative 2x plus 5, and it's all divided by h. Now if we simplify in the numerator, by distributing, we're going to get negative 2x minus 2h plus 5 plus 2x minus 5 all over h. The plus 5 and the minus 5 cancel. The negative 2x and the positive 2x cancel. So that leaves us negative 2h over h. H's cancel. So we have negative 2. And part B, similar. We have a quadratic function there in x squared. I'm going to start the same way. I'm going to say f of x equals x squared minus 2. So f of x plus h, the x plus h, the entire expression x plus h is going to replace that x in f of x. So instead of x squared, it's going to be x plus h squared minus 2. Now this expression here, x plus h to the second power, x plus h squared means x plus h times x plus h. And that's going to equal x squared plus 2xh plus h squared, and then we have so there's f of x. This right here is f of x plus h, and here we have f of x. So to set up the difference quotient, here we need f of x plus h right there, but that's just this expression. So I'm going to write that x squared plus 2hx plus h squared minus 2. So there's our f of x plus h. Now we need to subtract f of x, so minus x squared minus 2. And that's all over h. Now if we distribute the minus sign, we're going to have x squared plus 2xh plus h squared minus 2 minus x squared plus 2, the minus 2 and the plus 2. Oh, and it's all over h. Minus 2 plus 2 cancel. The positive x squared, the negative x squared would cancel. So we've got these two terms here, 2xh plus h squared all over h. Now in the numerator here, both terms, the 2xh and the h squared, they both have an h. So if you factor out an h, from the numerator you're going to have 2x plus h all over h. The reason for factoring out that h is you can cancel now. So the final answer is that 2x plus h plus h. Now, question 2 is also from chapter 2, section 2.2, and later on in the chapter, I think it's section 2.6, transformations of functions. It helps to have an idea of what a traditional square root graph looks like. So square root of x, the graph starts at 0, 0 and comes up and to the right. So we got to consider what these transformations do to the graph. So the plus 3 left, the minus 1 moves down, and then this minus sign out in front flips the graph upside down. So we got three transformations that are all going to change the way that graph there looks. So we're to draw a new graph and move it to the left 3 and down 1. So that's where I'm going to place my starting point. And then rather than the graph pointing up and to the right like a square root usually does, this one's going to point down and to the left. But we need to be a little more exact. We have to have the correct width. So I need to plug in a few values of x. Now I can't plug in anything for x. Like for example, I couldn't plug in a -4, because if I plugged a -4 in for that x, I get -4 plus 3, which is -1, and you can't square root -1. And I've already plugged in a -3, and that produced -1. That's just that point right there. So what if I did -2? Now if I plugged in a -2 for that x, I'd get -2 plus 3, which is 1. Square root of 1 is 1. And then you would multiply it by the negative sign, so you'd get -1. And then you'd subtract by this -1 to get -2. So -2 comma -2. Now knowing that this is a square root, I'm going to choose wisely my next x value. Oh, that point got it. There we go. -2 comma -2. If I chose to let x equal 1, for example, and I plug that 1 in for x, I'd get 1 plus 3, which is 4. Square root of 4 is 2. And then multiply it by this negative sign. So I get -2. And then -2 minus 1 is -3. So the point 1 comma -3 is also on the graph. Got a couple of points there. Okay. Now I'm going to do the same for part B. Typically, a square or an x squared graph, it's parabola. and the vertex is there at 0, 0. So doing the same thing, this, what does that transformation do? What does that transformation do? And what does that transformation do? Well, minus 4 inside the function is going to move right. Because remember, inside the function is opposite. This plus 3 is going to move up. And then that 1/2 is a stretch. Well, we could describe it a couple different ways. I'm actually going to describe it as, since it's outside the function, it's vertical. So I'm going to call it a vertical compression, would be technically the correct way of stating it. So vertical compression. So what you do is draw another graph. To the right 4 and up 3. So there's the vertex. Now, like with the last one, I'm going to just graph a couple of points. I already know the vertex is the point 4, 3. If I choose some points close to the vertex, 3 for example, an x value of 3, then if I plug a 3 in for that x, then 3 minus 4 is -1, but -1 squared is 1. And then 1 times 1/2 is 1/2. And 1/2 plus 3 is 3.5. So 3, 3.5. And then since a parabola is symmetric, and that point's reflected across on the other side of the vertex, this gives us a pretty good idea of the width of the parabola. And I did not hit any of the points. Let's try it again. A little better. Okay, part C. An absolute value function looks similar to a parabola. It's got a vertex at 0, 0, but it's not curved. It's a V-shaped graph. Okay. So we've got a transformation here, and a couple of them there. We got a -3 which flips it up, or a minus which flips it upside down, and a 3 which stretches it vertically. So this graph this +2 moves it to the left 2 units, and this -4 moves it down 4 units. So I'm going to redraw my graph so I can fit it on here. Okay, to the left 2 units, down 4 units. And I know that the graph's going to be upside down, but we have to have the correct width. So I can just make a few other points here. I know that one of the points is already -2, -4. So if I choose -1 and plug that in for x right there, then -1 plus 2 is 1. And the absolute value of 1 is 1. 1 times -3 is -3. And then -3 minus 4 is -7. So -1, -7. And like a parabola, the V shape is symmetric. Well, there you go. Part D. This is a transformation of what's called the reciprocal function. The reciprocal function is 1 over x, and the graph you can see here that x can't be 0, so there's a vertical asymptote right there at 0, and the degree of the denominator is 1, and since the numerator has no variable, it's considered degree 0. The numerator then has a smaller degree than the denominator, which means there's a horizontal asymptote at 0. And then the reciprocal function graph has two pieces, there and there. So we've just got to graph this same graph, but with these transformations. It's got to move down 3 because that's outside the function, and to the left 2 because that's inside the function. Now the one to the left is going to move the vertical asymptote 2 units. The one down is going to move the horizontal asymptote down 3 units. So horizontal asymptote is down 3. Vertical asymptote is to the left 2. And we have the graph. Okay, question 3, finding or writing equations of inverse functions. This is from section 2.8. Now the following functions are one-to-one. Remember that means that it would pass the horizontal line test if they were graphed. It also means that their inverses are functions. So to find the equation of the inverse, remember you switch the place of x and y, and then solve for y. So remember the f of x is just y. So to switch their place, you can write x equals negative 5y plus 4, and then solve for y. Get y by itself. And since we started with function notation f of x, we need to end as the inverse of f. And it's pretty much the same thing for the rest of these. You switch the place of x and y and solve for y. So this one, first call f of x and y, and then switch the place of x and y. And then solve for y. Last step here is going to be to take a cube root on both sides. So y equals cube root of x minus 2 over 4. Again, that's the inverse. Okay, this one's same technique. We solve for y is slightly different. So if f of x is equal to y, then we've got switch the place of x and y to get x equals 5 over negative y plus 2. Now this fraction here, I want to try to get y so that it's not in the denominator. So one thing you can do is multiply it on both sides. So now to get y by itself, it wouldn't make sense to distribute the x, because that's just going to put another thing with y that I don't want. I want to keep y and try to get y by itself. So rather than distributing the x, I'm going to divide by it. So now negative y plus 2 equals 5 over x. Subtract the 2. And then divide by negative. Divide the whole thing by negative 1 to get positive y equals negative 5 over x plus 2. That equals the inverse. Okay, and finally, part D, we're going to switch the place of x and y. So this y is going to become an x, and then both of those x's are going to become y's. And then similar to part C, I want to try to get rid of this fraction here by multiplying by the denominator on both sides. And then I'm also going to, in this case, distribute the x. So I've got y terms on both sides of the equation. I've got yx here, and I've got y. So I want to get the y's on the same side. Subtract this y over here. But then I want to move that x. I want to move that to the right side. So now on the left side I get yx minus y. On the right side I get negative 5 minus x. Now if you notice here on the left, both terms have a y. So you can factor it out, and you're left with x minus 1. And if you divide by it, you've got your inverse. Okay, page 3 is also from section 2.8, which is finding the inverse. This one's just, these inverses are going to be found graphically. So you still do the same way. You switch the place of x and y. So what would be best is to identify some points on the graph that go right through a coordinate. Like that one there is the point negative 5, comma negative 2. This point there is the point negative 3, comma 1. Here we have a point of 1, comma 2, 3, comma 3. Up here we have a point of 7, comma 5. So to find the inverse, you switch the place of x and y. So you switch all of these points. I'm going to have a point of negative 2, comma negative 5. And then if you want to switch that one, it's going to be 1, comma negative 3. Switch that point, it's going to be 2, comma 1, 3, comma 3, and 5, comma 7. And that's the inverse. If you remember from section 2.8, if you graph the function and its inverse on the same graph, they would be a reflection over that line right there, which is the case. Well, I guess we have to answer to determine if it has an inverse. That's using the idea of being one-to-one. So the original function, the one here in black, it passes the horizontal line test, so it has an inverse. And the one here, that's the one we just sketched, that is the inverse. Part B, we can do the same way. Try to identify points that go right through a coordinate. So the point 3, 1, 6, 4, looks like possibly 9, 9. So if we were to switch the place of those, this point here, 3, 1 becomes 1, 3. This point here, 6, 4 becomes 4, 6. Inverse would look something like that. Okay, question 5. This comes from chapter 3, section 3.4 and 3.5. Part A, we need to use the rational zero theorem. If you don't remember, that's the P and the Q. So for part A, factors of 6, remember those are P, and factors of the leading coefficient, that's Q. So for part A, if we wanted to do P divided by Q, well, first of all, let's do P. It's plus or minus 1, 2, 3, and 6. Now Q, the factors of Q are just plus or minus 1, and if you divide any of these numbers by plus or minus 1, it doesn't change the value of any of those numbers. So I'm going to call that my P over Q list. Those are my possible rational zeros. Now part B, we didn't actually talk about Descartes' rule of signs. But we can talk about it now. It's not a necessary rule. It can make things easier. So for part B, what Descartes' rule of signs has you do is count sign changes. So for P of x, I'm not going to include any terms, just the sign of the term. So the first term is positive, the second term is negative, and the third term is positive. So from positive to negative, here we have a sign change, and then it goes from negative to positive there, so there's two sign changes. And what that means is P of x, since there's two sign changes, could have two I'll write it here. P of x could have 2, and then you always decrease that number by 2 units. So if I start with 2 and I decrease that by 2, then it goes to 0, 2, or 0, positive zeros. If there had been 5 sign changes, then I would have stated it this way. P of x could have 5 or 3 or 1 positive zeros. You always go down by 2 units. You do the same thing for P of negative x. So if I were to plug in a negative x and then raise it to the third power, it becomes negative x cubed, so then the first term would be negative. If I plugged in a negative x for that x right there and multiplied it by negative 7, I'd get a positive 7x. So the second term would be positive. And then that positive 6 there is always going to be positive, so that's a positive 6. So there's only one sign change. It goes from negative to positive right there. So one sign change. That means P of x has 1 negative 0. If we're testing P of negative x here, that means we're testing for negative zeros. That's why I said it's negative zeros. So that's Descartes' rule of signs. Again, not super necessary. What it tells you is what your zeros could look like. Here it says we could have 2 or 0 positive zeros, and we have 1 negative 0. But we would have found that anyway just by finishing the problem and finding the zeros. Now, part C, the fun one. Factor the polynomial. So what we need to do is choose from our possible rational zeros and use synthetic division. So I'm going to start with positive 1. Now, notice there's a missing term. It goes x to the third and then minus 7x. We're missing an x squared term. So you have to have a 0 in its place. And then do the synthetic division algorithm. And we got a remainder of 0, which is a good thing. That means that the number we're testing, which is 1, turns out to be a 0. Now if it's a 0, that means the 0 is x equals 1. That means the factor is x minus 1. And these numbers give the coefficients. Remember, those numbers give the coefficients of the other factor. So that's going to be x squared plus x minus 6. Now this can be factored further into x plus 3 and x minus 2. So the full factorization is x minus 1 times x plus 3 times x minus 2. Now for part D, we need to sketch the graph. We have the 3 zeros, positive 1, negative 3, and positive 2. Now to find the y-intercept, I'm going to go back to the original. If I plugged in a 0 for all of the x's, I'd be left with positive 6. So positive 6 is my y-intercept. Now going back to the polynomial, it's degree 3. It's a third degree polynomial. What that means is the end behavior, left side is going down to negative infinity. Right side is going up to positive infinity. So we need to figure out how this left side here, what's it going to take to get those two sides to connect. So if I'm starting here on the left, when I get to this 0, I've got to decide, does it cross through or does it bounce? And the 0 comes from this factor, x plus 3. That factor has multiplicity 1. Odd multiplicity, remember, means that the 0 passes through, the graph passes through, so it crosses the x-axis. Now, I've got to figure out where the graph is at -2, because I don't know if it goes right to the y-intercept, or perhaps it goes up a little bit and then comes down through. So when x equals -2, if I plug in -2 in for all of those x's, I would get -3 times +1 times -4, and that equals 12. So when x is -2, the graph is all the way up at 12, about up there, so it goes all the way up to 12, comes down. Now when it gets to that 0 of x equals 1, that comes from this factor x minus 1, that has a multiplicity, it's got multiplicity 1, it's odd, so it crosses through. Now at some point it's going to have to turn back up and come back to that 0. Now between 1 and 2, in order to find out exactly how far down it goes, you'd have to test a decimal or fraction. So I'm not expecting you to do that, so it does come down and turn back up at some point and connect up with the other side of the graph. Now for question 6, same idea. It's a 4th degree polynomial. So the graph's going to look a little different, but everything else is exactly the same. For part A, again, since my Q value right here is just 1, dividing by 1 doesn't change the value of the number. So P over Q really are going to be my factors of 8. So that's plus or minus 1, 2, 4, and 8. Part B, for Descartes' rule of signs, P of x, the first term is positive, second term positive, third term negative, fourth term negative, and last term positive. So the sign change, we have positive to negative, and then we have negative to positive. So there's two sign changes. And since we're testing P of positive x, we're talking about positive zeros. If there's two sign changes, that means 2, and then you decrease it. Remember, decrease it by 2 units, so 2 or 0, positive zeros. Now P of negative x, if I plug in a negative for all of these x's, starting with the first one, x to the 4th, if I plugged in a negative x and then raise it to the 4th power, I'm going to get x to the 4th again, so it's a positive. For x to the 3rd, if I plug in a negative x and raise it to the 3rd power, I'm going to get negative x cubed. So that second term is negative. Third term here, if I plug in a negative x and squared, I get x squared, and then multiply it by -6. That's negative. Now here, with that x, if I multiply by negative 4 times negative x, that's positive 4x, that's a positive. And then the last term is positive 8. So I've got a sign change there from positive to negative, and then a sign change here from negative to positive. So two sign changes. And since we were testing p of negative x, we're talking about negative zeros. So two sign changes there means 2 or 0, negative zeros. Now starting part C, we got to factor the polynomial. And these are my possible zeros right there. So again, I'm going to just start at the beginning and test positive 1. And we have a remainder of 0. So one of my zeros is x equals 1. So then its factor is x minus 1. And then these numbers here give us the coefficient of x to the third plus 2x squared minus 4x minus 8. So I still have to continue factoring that into 3 more factors. So I'm going to go back to my P over Q list and just choose another one. I'm going to choose 2. And now I'm going to use the coefficients from that smaller polynomial, which are 1, 2, negative 4, negative 8, and then do synthetic division again. And got another remainder of 0, which means another factor, or sorry, another 0 is x equals 2. So now I've got 2 factors. I've got x minus 1, and then now I've got x minus 2, and then these coefficients are coefficients of the remaining factor, x squared plus 4x plus 4. This can be factored. Now remember, not every problem that we've done that look like this, not every time when you get to a quadratic can you factor it. Sometimes you have to use the quadratic formula. This one can factor though into x plus 2 times x plus 2. So then we have x minus 1, x minus 2, and x plus 2 squared. So there's the complete factorization of the polynomial. Now we've got to graph this for part D. So I've got a 0 at positive 1, at positive 2, and at negative 2. If I go back to the original polynomial and plug 0 for all the x's, then that leaves me positive 8 as my y-intercept. And since this is a 4th degree polynomial, the end behaviors are both going in the same direction. In this case, up. Left side's going up, right side's going up. And this particular 0 right here of negative 2, it comes from this factor, which has multiplicity that's even. It's got multiplicity 2, so it's going to bounce. When I come down to that 0, it's going to bounce off the x-axis. Now, I don't know if it's going to go right to there. Like on the last problem, it might come up a little bit and then come down. So I've got to find out what's happening when x equals -1. So we'll plug in a -1 for all those x's. -1 minus 1 is -2. -1 minus 2 is -3. And -1 plus 2 is 1. And 1 squared is 1. That multiplies together to be 6. So -1 comma 6. So it goes through -1 comma 6 to your y-intercept. Comes down to that 0. Now that 0 comes from this factor. It has multiplicity 1. It's odd multiplicity, so it crosses through. Comes back around and connects up with the other side.